Mr. Lee, in this video, we're going to go over series and parallel capacitors. Let's begin. So one of the things that we can do with capacitors is the idea of combining multiple capacitors together. Now, when you do this, several very interesting things can happen. One of which is that you could either make the overall capacitor for the circuit get bigger, or the overall capacitors for a circuit can actually decrease. You could lessen the overall effectiveness of the capacitor. So we're going to explore both of these conditions, and we're going to go over how the formula works, like the theory and the concepts behind it. And well, that's it. So let's begin. So the first thing that we need to start off with is the formula for capacitance. So it's C is equal to Q over delta V. So a capacitor, or the capacitance of a capacitor, is how much charge it can hold depending on the change in voltage. So let's do a little highlight there because we will be referencing this formula throughout this entire video. All right, so the first thing I want to go over is how you can tell the difference between a series and a parallel capacitor. And I'm going to draw it. I'm going to do the series one first. So series. So for the series, it's important to know that the charges have one path. Okay, so the charges have one path to follow. And when we get into the circuits unit, we'll give this a term, but I'll give this to you now. It's called current. But for all intents and purposes right now, let's just think of it as the path that it can follow. All right, so in order to draw a circuit, the first thing I want to do is I want to draw the EMF source. Okay, EMF is written with that fancy looking E, and this, you could just think of it as a thing that causes a change in voltage. Another way to think about this is like the battery. Okay, and we're going to draw a wire here, and then we're going to draw a line going down. Here we have a capacitor, and going down here we have another capacitor, and we're going to draw the wire, and we're going to continue going down like this. So here we have a complete circuit. Just so that we're all on the same page, I'm going to highlight this part right here. This is the EMF source, and I'm going to highlight my two different capacitors. So I have a capacitor here, and I have a capacitor here. Now, for the sake of this video, and just to make things a little bit more easy in terms of math, we will say that this EMF source is like a 9-volt battery, and each capacitor, so we'll call this C and C, they are both identical capacitors. Okay? Identical capacitors. Okay. So when I say the charges have one path to follow, I'll show you what I mean by that using a different colored ink. So if the charges are flowing, we can see that it only has one direction that it can go, or one loop. Okay, so one path, one loop, right? Whatever you want to think of it. Okay, there's no way for the charges to make a little detour. However, for parallel, charges have multiple paths. Okay, so let's start off with the sketch first. I'm going to draw my EMF source here. Draw my wire. I'm going to give this capacitor the first one. Okay, so that's my first capacitor. And let me show you the second one right here. This is my second capacitor. So to keep things aligned with the color coding, I'm going to highlight my capacitors here. Okay, there and there. And I'm going to highlight my EMF source right here. And we'll make the EMF source 9 volts as well, and both of those capacitors are identical. Okay, so what I mean by the charges have multiple paths is that all the charges can take either this inner path here, okay, or given the option, it can also take this outer path right here. And I don't like using the word decision, but that decision, okay, because charges don't really think, they just do whatever they do. It happens at this junction there. or it could be disjunction, depending on how you're viewing the flow of charge. Okay, so whenever there's a junction or a split in the wires, that's where the paths go from one path to multiple paths. Okay, so these are what parallel capacitors will look like. Okay, now to go into the formula behind all this, let's start off with the series one first. So right below it, because I want to make sure this is clear of any of your previous notes, I'm going to draw the identical circuit, like so. Okay. And just as a reminder, our EMF source is 9 volts, and both of these capacitors are identical. So here's a couple of things. In order to really help with this analogy, if you remember back when we were talking about voltage, we said that delta V is a lot like a change in height. And for the sake of this video, we're going to keep on using that analogy, where if this delta or where this EMF source has a change in or a change in voltage of 9 volts, you can think of that as 0 volts being the floor and the 9 volts being the ceiling. Okay, so that's a change in height. And because this long part of the EMF source, we call that the positive side, and this the shortened nub, that's the negative side. Okay, we can say that up here, let's just say that up here we have a 9 volt, okay, like the ceiling, and down here we have the 0 volt, like the floor. So when we are looking at this upper portion, we view it as 9 volts, and this bottom portion as 0 volts. Okay, so this EMF source shows us that we have a change in height, right? We have raised the ceiling to 9 volts, and each capacitor sees a change in delta V. So when we go from this top plate here to this bottom plate here, okay, what we're doing is we're introducing a change in voltage. So from there to there, it sees a drop. So because these have equal capacitance, we can say that after the first capacitor, half of the voltage has been dropped. So after the first one, we have a delta V of 4.5. So this capacitor here is a delta V of 4.5. And the reason being is because our total height is 9 volts. And so after each drop, we can split it up evenly by 2. Now, in any given problem, you'll have to actually figure out the delta V. But for the sake of understanding this conceptually, I'm making it equal. All right, so at this point that I drew here with the dotted line, that is the halfway point. So halfway is 4.5. After the next capacitor drop, we should have a total delta V of 0. So that must mean that this capacitor also has a delta V of 4.5 volts. All right. The reason why we're going into this is because that idea right there helps us come up with the next set of formulas. One thing is with this formula, C is equal to Q over V, right? I'm going to actually rewrite this so that is V is equal to Q over C. All right. So each of these voltage drops, we can say, I'm going to call this C1 and C2, but just so you know, C1 equals C2. Okay, so we can say that the voltage drop of 1 plus the voltage drop of 2 equals to the total voltage drop of 9 volts. So if I were to replace V1 and V2 with the formula, we can say the amount of charge stored on C1 over C1 plus the amount of charge stored on C2 is equal to the total charge of the circuits stored on the capacitors over the total capacitance. Okay, so if I were to just clean this up with what we know that Q and C are just identical because we have equal capacitors. We get this formula here. Okay, now from this formula, we know that we could just add up all the charges to give us a total charge, but it's the denominator that's important, and it's the denominator that gives us our formula. So the formula for capacitance for parallel or for series is the following: 1 over C1 plus 1 over C2 plus 1 over C3 plus 1 over Cn for number is equal to 1 over the C total. Okay, and so the more capacitors you add in series, the overall capacitance actually weakens for a series circuits. So weakens the more you add. And this is simply because the delta V is shared. The change in voltage is shared amongst each capacitor. All right, so now let's take a look at a parallel capacitor. So if we take a look at a parallel capacitor, using the same idea, knowing that this EMF source is 9 volts, we can see up here and up here, we can start off with 9 volts, and down here is the 0 volts, using the analogy of the ceiling and the floor. So that means that each capacitor sees the total drop of 9 volts. So this capacitor C1 in this case, will also see a voltage drop of 9 volts. And this C2 will also see a voltage drop of 9 volts. Okay. And you might realize that the voltage drop is equal to the EMF source, and that's very important. Okay, now to come up with the rules here. So we learned that as we add more capacitors in series, it got weaker overall. And that's because the voltage was shared. But here, the voltage is not shared. Each capacitor has its own voltage. So the idea here is that as you add each capacitor in parallel, the overall capacitance will increase. Okay, and so let's write that down. Add more C, then C total increases. It's a directly proportional relationship. Okay, all right. And well, yeah, I think that's about it. I'll see you next time. Bye bye.